Welcome to today's Copernicus Data Space Ecosystem webinar, where we will be exploring how to work with custom scripts with Sentinel Hub APIs in Copernicus Data Space Ecosystem. In this session, William Ray will introduce you to custom scripts and demonstrate how they can be applied with the processing API in Copernicus browser. And without further ado, Will, the stage is yours.
Thank you very much, Sabina. Hi everyone. Great to be here. As Sabina said, my name is William Ray. I'm a part of the education team at Sinergise. So today I'm going to introduce you to working with custom scripts with the Sentinel Hub APIs within CDSE. So what am I going to go through? I'm going to talk about, well, what are EvalScripts / custom scripts. I'm going to run through an overview of their structure. I'm going to run through plenty of examples. So I'll have a kind of examples-based approach to showing some of the functionalities within custom scripts. I'll then introduce you to the custom scripts repository. This is our online repository of custom scripts created by the community over several years, hosted on GitHub. I'll also then run through a couple of demos, so working with custom scripts in Copernicus browser, and then lastly, custom scripts in the requests builder application as well. And then we'll have some additional resources and time for some Q&A. Okay, so what are EvalScripts? Well, they're not so scary. They're actually just blocks of JavaScript code, which are used to perform operations on your input satellite data. So at a pixel level. They are part of any API requests within which are using Sentinel Hub. So that'll be the processing API or the statistical API. And you'd also use them as inputs if you're using the batch versions of those APIs as well. And they have a really standard basic structure. So what can you do? You can visualize a single band. You could create composites with specific color maps. You can also perform complex band calculations. So maybe something simple like NDVI, where it's a simple formula, but you can also create far more complex ones as well. You can also create land cover classifications using either some light machine learning models, for example, light GBM, or you could even take on a rules-based approach as well. You can also combine multiple data sources as well as multiple dates and create kind of new products from that. So maybe you would want to create a product combining Sentinel-1 and Sentinel-2, or you may want to create an aggregated product such as the mean or the median NDVI for a whole year, for instance. So you can actually pull in all the imagery from a year and then create a single output. So what does an EvalScript need? Well, there's several things that are specified alongside the EvalScript in your API request. So your data source, your date and time range, your area of interest or bounding box, etc., etc. But let's go a little bit more into detail about EvalScripts specifically. One note though, before we get going, EvalScripts only operate on a pixel level. So that means that we can't run any neighborhood pixel reliant analyses. So for example, if you had a digital elevation model, you can't generate a slope using EvalScript because currently the functionality doesn't allow you to rely on the neighborhood relationships between the pixels. So the structure, really simple. Here I've got just an RGB or true color image for Sentinel-2. So first thing you need to do is just specify the version of the EvalScript. Currently we're on version 3, and it's as simple as just typing out your / version equals 3, and that's it. You then have a setup function. This is a mandatory function to specify your input bands. You can see in this example, we call them band 2, band 3, and band 4. And then you also specify your output shape, in this instance, 3 bands. and the data format. So here the sample type is set as auto. This is for a processing API request, so automatically it's going to pick the unsigned integer 8 as your output. So it's values from 0 to 255, perfect for visualizing data. We then have a second mandatory function called evaluate pixel. And this is where you actually perform your required operations on a pixel level. So you can see here we have a really simple operation where we're just returning back the 4 band or the 3 bands in the RGB order. So band 4 is the red, etc., etc. You can also note here that the shape of the returned object in the evaluate pixel function matches the format of the output in the setup function. In addition, if you're creating more complex eval scripts, as we'll see a little bit later, you can actually create additional functions within the JavaScript itself, and then you can actually call those functions within your evaluate pixel function. And of course, yeah, the output for this, we have just an example here of what a true color image would look like. We can also start to color correct within eval scripts. So maybe you noticed in the image on the top right, it's kind of a little bit dark. To counter this, though, you can actually just multiply your outputs by 2.5 here, and even increase the contrast here. So we've got a 2.5 times the band minus 0.07. And you can see now we have a much brighter image, and actually a little bit more contrast as well, which makes it look far easier to look at, and obviously a little bit more attractive as well. So let's have a look at another example. The first one we're going to look at here is NDVI. Let's say we want to calculate NDVI from our Sentinel-2 data and then add an interpolated color map. So let's concentrate on calculating NDVI first. You can see we've actually changed our setup function here. We're now only using band 4 and band 8 from Sentinel-2. And our output has changed as well. So the shape is actually a single band. And we're now using the float 32 sample type for our raster output. And this is because obviously we're looking at a vegetation index, and the values are going to be from -1 to 1, most of them 0 to 1. And we're looking at actual float values, so like 0.001, 0.34, anything in between 0 and 1, rather than the full numbers that we're using in our 0 to 255 with untied integer 8. Yeah. And then in our evaluate pixel function, we now actually apply our an index function to those 2 bands. So you can see here in our return, we have index, and then open the brackets, we've got samples band 8 and samples band 4. And that automatically will run the formula, which you can see in the bottom left here, where you've got band 8 minus band 4 over band 8 plus band 4. And that will return our NDVI. We can then, additionally, if we want to add a color map, we can actually create another function here where we've got the value interpolate function. And using this function, we can then assign RGB values, still using float 32 in this instance, to our NDVI values. So we can actually then create a nice visualization like on the right here, where the dark greens are like higher NDVI values, and then the lighter greens are low NDVI values. We can also add Cloudmasks as well. So as I'm sure we all know, Sentinel-2 has the scene classification layer Cloudmask band. So in this eval script here, it's actually almost identical to the one previously. We've added the SCL band as our input. We still have a 3-band output now. We're using a sample type of auto. But then we actually have a little if statement within our evaluate pixel function. So we can see here that if SCL has a value of 8, 9, or 10, which relate to clouds. So I think that's high and medium probability of cloud cover, as well as cloud shadow. We then return those pixels as black. So you can see there in the if statement, we've got if 8, 9, 10 dot includes samples.scl. So referring to that band specifically, return 0, 0, 0. And then else, return the value interpolate function on the NDVI return up here. And this returns back this color map here. All the cloudy pixels are then black. So it's a really easy way to actually mask out the data you don't need. We can also add some transparency as well. So this example here uses NDWI to make water pixels transparent. So we now actually include band 8 of the Sentinel-2, no, sorry, band 3 of the Sentinel-2 data, so that we can calculate NDWI wetness index. And we're now actually outputting 4 bands to allow us to implement our transparency. And then we have our transparency value here, which is conditional on our wetness index. So we have here, if NDWI is less than 0, transparency equals 1. And then we use here in our return, it's now a 4-band output. We have 2.5 times our true color bands, so band 4, band 3, and band 2. And then in addition, we have our data mask band. So we have this defined as transparency. So what this transparency value here of 1 it means is that every time its condition is met, where NDVI is below 0, it returns back a transparent pixel. So you can see here that we have our area of interest like we've been looking at previously, and all these transparent pixels are obviously water. So we have the coastline here, and anything that's white is water. We can also use multiple time or multiple dates within our eval scripts. So let's have a look at how we can actually handle multiple scenes as an input. So if multiple scenes are available in your requested data range, there are a couple of ways or different ways that the eval script can handle this. So this is defined via the mosaicing option within the setup function. So by default, we normally use simple. And this means that all the scenes are flattened into a single scene for evaluation. So if you're using simple mosaicing, you're going to be using a single acquisition. This is also impacted by the sample order, which is within your API request. So by default, you're always going to look for the most recent image, but you also have the option to look at the least recent or the least cloudy as well. But if you use simple mosaicing, you're going to always use the most recent image if you don't change anything explicitly. We then have orbit. This is where scenes are flattened, so that you have one sample per pixel per orbit, which is usually every 5 days with Sentinel-2. And then you have tile, and this is unflattened, so all the data can be passed into the evaluation. So there are some instances. It's not particularly common with the Sentinel missions, but if you're looking at, say, Sentinel-1 data up in the polar regions, you sometimes get more than one acquisition per day. And tile will give you the option of using multiple acquisitions per day. There is much more detail about these different mosaicing types within the CDSE documentation. So I would encourage you to go and read that and find out a little bit more detail about what's going on. But what's most important today is that to define these different mosaicing types, you can just add your mosaicing, semicolon, and then which one you're using, so orbit, simple, or tile, here within your setup function. So let's have a look at some examples, maybe just to make this a little bit more clearer. So we have here, we've got some area of interest on the east coast of Italy. We have our Sentinel-2 bounding box. And we're looking for a month of data between the 1st of March and the 31st of March 2024. And we have 12 Sentinel-2 scenes found during this period. So if we use this eval script here with simple mosaicing, only one scene is passed to the evaluate pixel function. And that's what's returned here. So you can see, yeah, we've got some cloud in our most recent image, but that's it. We could then change the API request to use least recent or least cloud cover, and we would probably get a different return. However, if we change this to mosaicing orbit, as we remember, this returns back a one scene per day. And then we actually start, that means that we're going to get 12 Sentinel-2 scenes that are returned using the evaluate pixel function. So how do we get an RGB image for a single date? Well, we can use an index. So in our returns here, we have samples. We then are using the 12 sample here. So we start at 0, remember, and return back the band after that. So this is returning back the most recent of those acquisitions, but you could change this. It's up to you. So you could put anything from 0 to 11, and you'd then see the returns would change here. So we can see here that the 11th one has returned actually only half the area of interest, whereas the 6th one is a little bit hazy, but you have the full area of interest. So that's one way you can manipulate the returns using the different mosaicing parameters that are available to you. In addition, you can create some multi-temporal products. So in this example, we're going to calculate the mean NDVI over a period of time. So firstly, our API request, just to reiterate, we have our bounding box set, which is defining the pixel areas or a pixel area returned, and also our date range, which is from the 1st to the 31st of March again. We have set the mosaicing to orbit so that we can use multiple scenes. We've then defined a function to calculate NDVI. You can see this is outside of our evaluate pixel function because we're actually going to call it a little bit later. So you can see here, we've actually explicitly defined it this time. So sample band 8 minus band 4 divided by the two bands added together. And then the return is NDVI, which is set up here. We then will then use this in our evaluate pixel function. So firstly, we loop through all the scenes in our time period using this little snippet of code here. We also have just a data mask input here so that any pixels that have no data aren't used in this calculation. So we then have NDVI equals the calc NDVI samples I, and the I actually stands for all the variables that are looped through here. And then we actually return back the average. So the average is actually defined by the sum divided by the count. So the sum is the sum of NDVI. And we then basically add each timestamp onto each timestamp until we finish our loop. And then we divide it by the count of the number of samples or the number of acquisitions in that time period, calculating the average or the mean of NDVI. In addition, we also have some flexibility with our PreProcessScenes function. This allows you to select scenes only from given dates. It's an optional function which can be run automatically before the data is accessed. And this can be used to specify, say, a specific date you may be interested in. So maybe you have a significant date where some change has occurred. So maybe a wildfire or land cover change, deforestation, that kind of thing. Where you can, and then you can actually explicitly say, I want to use this date and this date, and then look at the difference. You can also specify months to be taken into account. Maybe you're only interested in the growing season for a particular crop type. So then you can actually exclude fallow periods. So maybe data from November to February is of no use to you. So you can actually then explicitly say the months that you're most interested in. And then also you can specify allowed time periods within your API request. So an example of this would be finding the difference in NDVI between the 10th of March and the 13th of June 2023. You can then see here in our EvalScript, we've now got this allowed dates variable. So we've picked an image from the 10th of March and the 13th of June. So maybe you're thinking, like, how do I automate this? Or like, what's the purpose of this? Like in this particular case, there's some pre-knowledge of the data is probably needed. So the writer of this script maybe had already looked at some of the imagery and was like, okay, these are my best images that I can use to detect the change. Like the 10th of March is the closest cloud-free image to my date of interest, and the 13th of June is just the closest date or the most significant date for me. So then you can use these two dates and then calculate the difference here. So again, it's actually really simple in the evaluate pixel function. NDVI difference equals the NDVI of sample 1, which is actually the second sample, so the most recent, minus the NDVI output from samples 0, which is the least recent sample. And then you just return the difference. And here's our output here. So you can see some of the positive difference and then some of the negative difference. You can also add some color, as we saw actually in probably one of the first examples, to your returns. So here we're looking at NDWI as well. We can create a color map. Sorry, just lost my words. We can create a color map with our colors here in hex and then assigned to a value. So we have a color here assigned to values between -1 up to -0.75, and then so on, so forth. And then you can actually calculate your NDVI difference again here, like we did previously. We have a watermask again with NDWI. And then our return is actually the image vals, which is generated as the visualizer on the NDVI difference. And then we return back the image vals. And then our data mask is if NDVI is below 0. And this then returns back this example here. So we can actually visualize the difference a little bit better this time. So yeah, to wrap things up on the slides, some of the examples of what you can actually do with your eval scripts. Here we've got more of a visualization. We're looking at like it's named as the aesthetic neon script. It's a script that's really good at highlighting urban and desert environments. You can also combine data sets to map multi-temporal change. Here we're looking at how you can map forest fire progression using Sentinel-2 and Sentinel-1. Like, why would you do that? Well, sometimes your acquisitions, maybe they're not frequent enough. Maybe some of your Sentinel-2 may be affected by cloud cover. So if you can combine Sentinel-1 and Sentinel-2, you can actually then create a fuller picture, and you can actually see the difference between, say, the wildfire at the first timestamp and then where it's actually spread to on the second timestamp. You can also track variables such as the radar vegetation index, calculate it, and then visualize it in a nice, easy to interpret way here to track agricultural development as well. But probably what's most interesting to all of us is probably how we actually utilize these in Copernicus browser and Request Builder. So I'm going to switch over to my browser now, and we'll have a look at some examples there. So let's start in Copernicus browser. We already have some EvalScripts already predefined, as I'm sure you have all tried out before. So we have just your true color here by default. We then have NDVI, for instance, and the shortwave infrared visualizations. But how do we actually create some more interesting like custom creations? So we can actually go down here to custom. We already have composites where we can actually create a RGB. So if we wanted just an RGB image, we'd go to like band 4, band 3, band 2, and we have a true color image. So that's just a nice GUI interface. We also have index calculators, but what's most interesting is the custom one here. And this actually shows us the code that was used to generate this visualization. So we can actually make it a little bit bigger and play around with this on the fly. So maybe let's multiply this by 4.5 instead, rather than 2.5, and then we can click apply. And then actually on the fly, we're actually changing our image. So we can see we've returned back brighter image again. Let's try and break this time. Let's go 10 instead. And yeah, now we're super saturated. So it's not such a nice image to look at, but this gives you an idea of how you can play around with a script live within Copernicus browser. So in addition though, what's really cool is that you can actually navigate to the custom scripts repository. This is found at customscripts.sentinelhub.com. You can then find a custom script you're interested in. So let's have a look at Sentinel 2. You can see here that we have absolutely dozens of visualizations here that we can look at. Let's take a look at a snow classifier. So we can see our EvalScript here. There are two ways we can do this. We can either copy and paste it from here, or we can actually look at a nice example in Copernicus browser. So I'm going to click on the Copernicus browser link. This is going to take us to a new page for Copernicus browser. You can see here that our EvalScript has been loaded up straight away. We're actually loading it from the URL. And we've been zoomed into a nice example here already. I think this is in Slovenia by the looks of things. And we can actually start playing around with the dates. And we can see how things change. So we can actually go back to the custom scripts repository and maybe find out a little bit more about this EvalScript. So we can scroll down to the general description and we can then read into what's going on. So it seems that just the bright pixels are snowy pixels. So we're not actually looking at maybe different individual types of snow cover. But let's have a look at Sentinel 1. Let's maybe pick up the urban areas one, for instance. Let's copy and paste this. Go back to Copernicus browser. We're going to switch over to Sentinel 1, like so. Find our latest acquisition. Our nearest big city will be Ljubljana. Oh no, it's not. It's a grep. I've gone past Ljubljana. Okay, but now if I look for the latest Sentinel-1 image, I can go to the custom scripts part here and paste in that eval script we're looking at and click apply. And then we can load up our urban visualization that way. So our kind of bright green and bright pink pixels are kind of the urban area for Zagreb. And we can actually bring in the Sentinel-2 mosaic on top, just to confirm. Turn this off, there we go. So you can see there, but yeah, we're detecting our urban areas really nicely. Okay, but lastly, let's have a look at the request builder application. So for that, let me just find it. There we go. Okay, so for this, you'll need to be logged in to your CDSE account for sure. But if we scroll down here, we can see our EvalScripts box here, very much similar to the browser. Let's just send a request just to see what is returned. So we have a nice true color image there, but we can actually then adjust it either manually ourselves, or we can even call our own data products. So if I click here now on data product selection, this is actually automatically generated depending on your data collection. So Sentinel-2, we have a lot of our vegetation indexes. Let's have a look at red edge NDVI. We can then see our available products. So we have a grayscale, a blue-red, green-white, red-white, red temperature visualization. Let's go for red. And then we can see our eval script. We can then click select, and it's automatically loaded into our eval script parameter. We can then send it, and then we can see what our return looks like. If we want, we can actually then start playing around with the return. So maybe we're interested in making it a little bit brighter. So we could say bright equals val multiplied by 2.5, for instance. And then if we change this to bright, this should return back a nice bright return. And not quite. I've obviously got an error somewhere. Let's see if that works, but if not, yeah. That's the joy of a live demo and trying something. But let's return back to the presentation. And just to wrap things up, I've got some useful links for you. So obviously we all know about the Copernicus browser. There's a link here to the EvalScript documentation that I encourage you to read through. There's a lot more functionality than I've talked about today. That is in the process of being updated. So you should hear about this in probably the next CDSE newsletter. And there also will soon be a couple of example Jupyter notebooks that let you interactively learn about eval scripts as well. We then also have a link to the custom scripts repository. We encourage you to subscribe to the newsletter, and obviously you have access to the Copernicus Database Ecosystem Gallery and the forum where you can ask any questions, and we'll always be happy to get back to you. But I will pass you back to Sabina for some Q&A.
Thank you, Will, for a great presentation, as always. So let's check our questions. We have a question from Anna. So she wrote that she understands it operates at pixel level, but is it possible to do the processing only for her area of interest and not the whole scene?
Yes. Yep. So I didn't allude to it too much because we're concentrating on the custom script, but within your API request, you specify either your area or a bounding box. So you're never having to process the whole Sentinel-2 scene. In fact, there is actually a limit of 2,500 by 2,500 pixels with the processing API. The whole point of the Sentinel Hub APIs, the ethos is that you only access the pixels that you need and only process the pixels you need. So as you saw in the inputs of our setup function, some of the time we're only calling 2 bands. So as well as not having to access the whole scene spatially, you also don't need to access the whole scene spectrally as well.
Thank you. We had another question if we can share the presentation with attendees, and I think it is possible for us to upload it somewhere and we can share it in the description of the recording when we will publish the video on the YouTube channel.
And I can add that all the examples that were shown in the presentation will be added to the documentation site very soon as well.
Then we have another question in the chat. Is there any index used to compare pre and post-earthquake data for detecting building damage?
As far as I know, not for building damage. It's something that you could develop if you want. But yeah, currently that's not something that is available in the custom scripts repository. There are some examples of like change detection algorithms within that, but not building damage specifically. It's probably much more difficult to do with Sentinel data, just due to the coarser resolution. So you probably want to be using commercial satellite imagery to detect building damage, for instance.
Yes, I just wanted to add to the question about pre and post earthquake differences that in Sentinel Hub you can't have access to Sentinel-1 interferometry typically. So ground deformation is not a data set that's readily shared directly with the Sentinel Hub APIs. What you can see is the effect of the change in the surface. And for that, you can either compare simple backscatter variables using a pre and post earthquake visualization in Copernicus browser, use the compare mode, or we have this custom script, which is actually a Sentinel-1 multi-temporal backscatter coefficient composite. So it's not specifically for earthquakes and buildings, but one possible application of this script, I think, is checking for earthquake damage.
Thank you, Andras. Then we have a question. Is there a data cube functionality available?
For that, I would look into OpenEO, for instance. You can, for sure, use the processing API to create data cubes using Xcube. I haven't got an example to hand, but I can show you. It's probably kind of outside the focus of this webinar.
So we can also answer additional question which came by Idris. They are particularly interested in understanding how Copernicus data can be used for temporal sediment monitoring, dispersion tracking, and sediment change detection along coastal areas. If you can elaborate on the tools or workflows available for this type of analysis.
So to answer that question is that I'm not really an expert in coastal area monitoring. However, I would encourage you to go to the custom scripts repository. Within Sentinel-2, a lot of our EvalScripts examples are split up by theme, and it should be some coastal specific algorithms that may be of interest to you.
So let's wait a couple of seconds if anybody else would have another question. In that case, I would like to thank you for joining us today for today's webinar. We hope it gave you useful insights into the custom scripts. If you will have further questions, you can, of course, feel free to continue the discussion on the CDSE forum. I would also like to use this opportunity to invite you to our next webinar, which will be held on November 12th, focusing on investigative journalism supported by Copernicus data. So for that, please follow us on social media channels for the official announcements and updates, and we look forward to seeing you there. Thank you, Will, for your presentation today, and Andras for your help, and see you the next time.